This is a production of the Chemical Education Material Study.
The world's oceans contain at least small amounts of most of the chemical elements. Some of the chemical species that occur in seawater are tabulated here with their relative molecular concentrations. In recent times, chemists have attempted to extract some of these elements for man's benefit, in much the same way as valuable ores are mined on land. One of the chemicals that is much used in our society is elemental bromine. Yet it occurs in seawater in the form of bromide ions in only very minute concentration, 15 ions per million molecules of water. Can the element bromine be extracted economically from seawater? The answer is yes. But how? What sequence of chemical reactions is used? To answer this question, we first explore some of the properties and chemistry of bromine. Here is a sample of the element, molecular formula Br2. Because of its high vapor pressure, bromine evaporates readily even at room temperature, forming a colored gas. Bromine is highly irritating and toxic. Special precautions must be taken in handling it, including rubber gloves and an exhaust system. Note that the gas is more dense than air. How does bromine react with some common elements? First, we try nonmetallic red phosphorus. The product of the reaction is phosphorus tribromide. The heat generated causes fumes. Now let's see how bromine reacts with the element hydrogen. We pour out a sample of bromine. Since we will be dealing with gaseous, not liquid bromine in this experiment, we can dispense with the gloves. A large beaker is heated so that when bromine is poured into it, the liquid vaporizes and fills the beaker with gaseous bromine. Let's turn on the hydrogen and light it. In the air, the pale blue flame of burning hydrogen is hard to see. But look what happens here. The flame continues to burn in the bromine vapor. Hydrogen reacts with bromine, forming hydrogen bromide. Now, to another sample of bromine, let's add aluminum. Not much happens at first. But once the oxide coating on the aluminum is penetrated, the two elements react vigorously. Similar experiments would show that bromine reacts with most elements. Here, the aluminum and bromine combine to form aluminum bromide, which, when purified, gives this solid. Is this bromine compound soluble in water? When water is added, a vigorous reaction occurs. Bromide ions are released into the water. Here's the purified product from the phosphorus and bromine reaction. Phosphorus tribromide, a liquid. Again, we'll add water. The reaction starts slowly, but soon gives off so much heat that bubbles of steam are formed. The reaction continues until all the phosphorus tribromide is gone, again releasing bromide ions into the water. This bottle contains pure hydrogen bromide, the product of the earlier reaction between hydrogen and bromine. When we let hydrogen bromide come in contact with water, the water level rises rapidly, indicating hydrogen bromide is very soluble in water. The net reaction is HBr gas gives hydrogen ions and again bromide ions. Because most inorganic bromine compounds are soluble in water, virtually all of the world's bromine is dissolved in the oceans or trapped in underground brine deposits as bromide ions. But what about the solubility of bromine itself? When bromine is added to water, it settles to the bottom, indicating that it is more dense than water. Now we'll mix the bromine and water with the help of a magnetic stirrer and a plastic-coated magnetic stirring bar. Vigorous and prolonged stirring gives us a saturated solution. The brown color is characteristic of aqueous bromine solutions. However, some drops of bromine remain undissolved. This indicates that elemental bromine is not highly soluble in water. What are some of the chemical properties of this aqueous solution? Let's divide the saturated solution in order to check the effect of varying the acidity. To this flask, we add acid. The color does not change appreciably. A base, sodium hydroxide, is added to the other flask. The bromine solution turns a very pale yellow, indicating that a reaction has taken place. Analysis shows that addition of hydroxide ions forms bromide ions and hypobromous acid, both colorless. Is the reaction reversed when acid is now added? Yes. As the concentration of hydroxide ions is lowered, the bromine color comes back. So bromine, in aqueous solution, can exist in different forms which are in rapid, reversible equilibrium, readily shifted by changing acidity. Now let's try to obtain elemental bromine from seawater, making use of our knowledge of the properties and chemistry of bromine. We shall use seawater concentrated by a factor of about 50 to make color changes more visible. The absence of any brown color indicates that no great amount of elemental bromine is present. When we check the acidity, the litmus turns blue. Seawater is basic. Since seawater contains hydroxide ions and also bromide ions, perhaps the equilibrium we studied earlier exists. If so, by adding acid to lower the hydroxide concentration, we should be able to produce elemental bromine. Let's find out. When acid is added to our sample, there is no visible color change. Therefore, no visible amount of bromine has been produced, even though the solution is acidic, as indicated by the litmus. There is actually almost no hypobromite in seawater, only bromide ions. So how can we change the bromide ions to elemental bromine? From the formulas, we see that 2 bromide ions can form a bromine molecule by losing 2 electrons. That is, the bromide ions must undergo oxidation. To find an oxidizing agent, we refer to a set of E0 reduction potentials. The tabulated reduction potential of bromine to bromide is 1.07 volts. We note that the tabulated E0 value for oxygen as an oxidizing agent is plus 1.23 volts, which makes it a stronger oxidizing agent than bromine. Furthermore, oxygen is the cheapest oxidizing agent. Let's find the E0 value for the overall reaction. We reverse the bromine reaction and change the sign of E0 to get the E0 value for the oxidation of bromide to bromine as minus 1.07 volts. The E0 value for the oxygen is plus 1.23 volts. For the sum of these half reactions, E0 is plus 0.16 volts. The positive value indicates the reaction should occur if all concentrations were 1 molar. But the bromide is so far below 1 molar that appreciable reaction is unlikely. Let's try anyway. We bubble pure oxygen through the solution. There is no visible effect. Apparently, the concentration of bromide ions is too low to produce any visible amounts of bromine. So we again check our table for another cheap but more powerful agent to oxidize the bromide ions. Here is chlorine. It is relatively inexpensive. As before, we calculate the E0 value of the overall reaction. The net reaction has an E0 value of plus 0.29 volts, almost twice that with oxygen. So the oxidation of bromide by chlorine is much more likely to proceed. We can check this reasoning by experiment. We'll add chlorine to concentrated seawater in an attempt to produce bromine. It works. The color gets deeper and deeper as more and more bromine is produced. The addition of chlorine has resulted in an aqueous solution of elemental bromine. Now, how can the bromine be extracted from this solution? Let's compare it with a stoppered flask of aqueous bromine from our earlier experiment. A considerable amount of volatile bromine has accumulated in the airspace above the solution because of the low solubility of elemental bromine in water. The high volatility suggests that if bubbles of air are forced through the solution, they will carry away bromine gas. A source of compressed air is connected to a dispersion tube. The air bubbles do sweep the volatile bromine out of solution. However, to concentrate the bromine from this dilute gaseous mixture, we'll need more controlled conditions. Here is another portion of concentrated seawater, this time in a system designed to handle the gaseous bromine. We first acidify the seawater. When the solution is chlorinated, elemental bromine forms. The compressed air sweeps the bromine out of the solution. If we try to collect the bromine in a beaker of water, you can see that very little of the bromine dissolves. As we should have suspected, the solubility of bromine in water is too low to allow us to concentrate it by this method. To find an effective method of concentrating the bromine, let's consider the solubilities of many bromine compounds in water. Hydrogen bromide is highly soluble, as we saw in the earlier experiment, so a large amount of bromine can be present in water as hydrogen bromide. But how can we convert bromine to hydrogen bromide? In HBr, the oxidation state of bromine is -1. The Br2, therefore, must undergo reduction. Here is a half reaction. Sulfur dioxide has been found to be the most economical reducing agent. Here are two half reactions. We add them to obtain an equation for an overall reaction. Then adding the appropriate E0 values gives a positive figure, showing that the overall reaction is spontaneous. We expect that an aqueous solution of hydrogen bromide will be produced, so the gaseous bromine, when swept out of the seawater, can be concentrated as aqueous hydrogen bromide. We have modified the apparatus to attempt the reduction of bromine with sulfur dioxide. The compressed air is again turned on, and elemental bromine is swept out. The sulfur dioxide is added through this tube and mixes with the bromine and water vapor coming down the column. The bromine color disappears, and colorless hydrogen bromide gas is formed, which passes into the water in this receiver. After a few minutes, the seawater solution loses its color, showing that the bromine has been swept out. Because of its high solubility, the hydrogen bromide which was formed should have collected in the water in this receiving flask. To check this, we again bubble chlorine through the solution. The characteristic color of aqueous bromine appears. The bromide ions in the hydrogen bromide solution are oxidized by chlorine to produce elemental bromine. Thus, we have succeeded in concentrating the bromine from the seawater into a much smaller volume of solution. Since our goal is to obtain elemental bromine, how do we now remove the bromine from the water in which it is dissolved? We could sweep it out with air, as we did before, but to minimize loss of bromine into the air, we'll use live steam, produced in this flask. The steam condenses as it passes into the solution, raising the temperature. Because bromine is more volatile than water, bromine distills from the solution. Relatively pure bromine condenses and collects in this receiving flask. On a laboratory scale, we have succeeded in obtaining this small quantity of bromine, less than 1 gram, from this large volume of seawater. Industry worldwide extracts more than 40 million pounds of bromine from seawater every year. The seawater enters a channel and flows past screens which prevent marine life and debris from entering the plant. Now, recall our laboratory procedures as we look at the industrial process for extracting bromine. In this large green pipe, the filtered water is acidified with sulfuric acid. Near the top of the pipe, chlorine is added to oxidize the bromide ions. The chlorinated water is then divided into many small streams. From here, the water falls as spray through this brick tower. Huge quantities of air are forced in at the bottom of the structure to sweep out the bromine vapor. The air and bromine vapor leave through this large green pipe. The small white pipe introduces sulfur dioxide gas to reduce the bromine vapor. The hydrogen bromide which is formed is concentrated in this absorption tank by dissolving in a falling spray of water. The concentrated hydrogen bromide solution then enters this tower, and chlorine is added to reoxidize the bromide. Steam is used to distill bromine from the solution. The bromine is now condensed to a liquid which can be stored for later use. So the industrial process of extracting bromine from seawater follows our laboratory chemistry. Starting with acidified seawater, chlorine is added to oxidize the bromide ions. This yields a dilute aqueous bromine solution. Air sweeps out the bromine, and sulfur dioxide gas in the presence of water reduces the bromine to bromide. Highly soluble hydrogen bromide gas is formed and absorbed in water. In this final step, chlorine gas is used once more to oxidize the bromide ions. The bromine is then distilled by steam, giving us the element bromine. For more than 50 years, the biggest use of bromine was in leaded gasoline, which made for smoother combustion, but released toxic lead bromides into the air. Leaded gas is a classic example of using a technical development without considering the environmental results. Subsequent restrictions have greatly reduced the use of leaded gas. And our highways are much less toxic. But most bromine compounds are not toxic and are still much used in fire retardants, pesticides, pharmaceuticals, photography, and drilling for oil.